Hello. Today we're going to discuss about chemical equilibrium. In a chemical reaction, the chemical equilibrium is the state in which both reactant and products are present in concentrations which have no further tendency to change with time. Usually, this state results when the forward reaction proceeds at the same rate as the reverse reaction. The reaction rates of the forward and backward reaction are generally not zero, but equal. Thus, there are no net changes in the concentrations of the reactants and products. As such, a state is known as dynamic equilibrium. Okay, at this point, let us take a look on the historical background of chemical equilibrium. The concept of chemical equilibrium was developed after Berthollet in 1803 found that some chemical reactions are reversible. For any reaction mixture to exist at equilibrium, the rates of the forward and the backward or the reverse reaction are equal. In the following chemical equation, with arrow pointing both sides to indicate chemical equilibrium, where A and B are the reactants and C and D are the product species. And the M, N, X, and Y are the stoichiometric coefficient of the respective reactants and product. The equilibrium position is said to be par to the right if the equilibrium nearly all the reactants are consumed, where A and B are converted to your C and D. The length of the forward reaction is greater than the rate of the backward reaction as indicated. So conversely, the equilibrium position is said to be far to the left if hardly no product is formed from the reactant, meaning the forward reaction takes shortly and only negligible amount of the reactant or the product rather are produced, and yet the backward reaction takes place. Okay, moving on, when in 1865, Goldberg and Wage, building on Berthollet ideas, proposed the law of mass action, where they said that the forward rates is proportional to a constant wherein taking the product of the concentration of the reactant, where the forward reaction will proceed if there is enough reactant A and B producing product C and D. Likewise, the backward reaction would take place if there is enough product C and D producing the reactant A and B. Okay, where K, F, and K sub B are constant of proportionality that will replace the parameter constant at the temperature is held constant, the nature of the reactants involved, and other parameters that would affect the rate of reaction. Where your A and B, C and D are active masses, where K and F are rate constant. Since the equilibrium forward and backward are rates are equal, therefore we can say we can equate these two reactions to be equal to each other. And we can take the ratio of Kf to Kb as the product raised to the respective coefficient as in this reaction, balance reaction, where Y is the coefficient of product D over the concentration of the reactant A raised to its coefficient M and times the reactant B raised to its coefficient N. Okay. This ratio is sometimes called as the quotient, the reaction quotient. Okay. So the ratio, the rates of the constant is also called reaction quotient Q, now known as equilibrium coefficient or constant. Okay, so the equilibrium constant KEQ, which is the ratio of the constant Kf over Kb, can be replaced by the expression KEQ. Okay, so we have the product in the numerator and the reactant in the denominator raised to their respective coefficient in the balance equation. Okay, so your KEQ, you have the product raised to its x and the product D raised to y, the coefficient AA raised to m. Okay. Moving on, What does this value KEQ will indicate? Okay, the value of KEQ shows that the extent to which the reactant are converted to product. If the KEQ value is very small, less than 1, okay, the forward reaction occurs very slightly. Okay, that is, the forward reaction occurs very slightly before equilibrium is established. So that means hardly any product are formed and yet equilibrium is already attained. So in the previous slides, we have these reactions, relationship. Okay, the first, if the KQ is very small, okay, hardly any product is formed from the reactant. So the rate or the extent of the forward reaction is negligible, very slightly, and yet equilibrium is already established. Okay, in this case, we can illustrate it in a form of equation where the arrow is shorter, the forward arrow is shorter than the backward arrow, meaning the KQ is very small. Now, the second, if the KQ is very large, greater than 1, the original reactants are largely converted to products. Therefore, the reaction proceeds almost towards completion. In this, if we can illustrate it in a reaction, the length of the forward arrow is longer than the length of the backward arrow, meaning the reactants are converted to products, and the reaction is far to the right before equilibrium is attained. Okay, let us have an example to illustrate the significance of the KEQ value. So here we are asked to identify which of the following reaction will tend to proceed almost towards completion. Again, to recall, if the KEQ value is very small, less than 1, hardly any products are formed and equilibrium is already established. And the KQ is greater than 1, the original reactants are largely converted to products, hence the reaction proceeds almost towards completion. Here's for number 1, for 2 moles of hydrogen bromide, giving you hydrogen gas and bromine gas, the KQ value is 7 times 10 to the negative 24. The KQ value is less than 1, very small. Therefore, it will not proceed almost towards completion. For number 2, you have ethyl with hydrogen will give you ethane, and the KQ value is positive 19. This is greater than 1. Therefore, the reaction number 2 will proceed almost towards completion. And for number 3, we have 2 moles of nitrogen oxide and oxygen gas will give you 2 moles of nitrogen dioxide. The KQ value is 3.4 times 10 to the positive 13. Again, this value is very large or greater than 1. Therefore, the forward reaction will proceed towards completion. For the fourth example, we have here 2 moles of methane would give you ethane and hydrogen gas. The KAQ value is 9.5 times 10 to the negative 13. Again, this value is less than 1. Therefore, this reaction will not proceed towards completion. Okay, the next topic is writing equilibrium constant or the KEQ expression. The KEQ, let us recall the equilibrium constant KEQ, referring to the balance equation, wherein you have the m moles of A plus n moles of D producing reversibly x moles of C and y moles of D. The reaction is reversible. So writing the KQ from the derivation from a while ago, okay, we have the KQ product raised to the respective coefficient over the reactant raised to its coefficient. Okay, where the bracket is a concentration in mole per liter. Okay. So the equation shows that the concentration are raised to the power corresponding to the coefficient in the balance equation. And this is the law of chemical equilibrium. So we have here guidelines for writing equilibrium constant expression. Number 1, only the gaseous or aqueous substances are considered in the expression for KEQ. Number 2, when pure substances such as liquid or solids are involved in the equilibria, Their activities do not appear in the equilibrium constant because the density of solids and liquids changes very little with a change in temperature. Their concentration will not change as the reaction proceeds. Hence, the numerical values are considered 1. And thirdly, the equilibrium constant is a dimensionless quantity. And in quoting a value for equilibrium constant, we must specify the valence equation and the temperature. Hence, the KQ value or the equilibrium expression is only true for a given balance equation and at a given temperature. So if the temperature is changed, the KQ value also changes. Okay, let us have an example in writing the expression for KQ. Say in the reaction of nitrogen and hydrogen forming ammonia. Okay, we check if the equation is balanced to follow the formula in writing the KEQ, where you have the product over the reactant in the denominator. Okay, we have 2 nitrogen, 3 times 2, we have 6 hydrogen. Hence, the product is raised to 2 for ammonia, which is the coefficient of ammonia, following this formula. Then, over the reactant, nitrogen raised to 1, which is the coefficient here, and hydrogen raised to 3, which is the coefficient of hydrogen in the balance equation. Okay, moving on, we have here mercury in liquid state and chlorine gas, giving you Hg2Cl2 in solid form or mercury chloride. Okay, you have 2 moles of mercury and 1 mole of chlorine producing 1 mole of the product. Again, since it says in the rule that only gaseous substances are considered in the expression for KEQ, for liquid and solids, the activity is considered to be 1. Okay, since the activity does not change with a change in temperature. Okay, so since the product is solid here, we don't have a value here except 1 because solid is taken as 1, the activity. Okay, for the reactant here, we have only chlorine. The mercury is not included because it is liquid. Okay, any number multiplied by 1 is the number itself. So the expression for this reaction is 1. The KQ expression is 1 over the concentration of chlorine. Okay, since the coefficient of chlorine here is 1, you don't need to write the exponent. Okay, moving on for the third one, we have here hydrofluoric acid and water liquid will give you the hydronium ion, H3O positive in aqueous, and the fluoride ion in the aqueous state. Okay, and this is an heterogeneous equilibria. Okay, so the product, the hydronium ion H3O positive is written. Okay, we have a balance equation here. We have 3 hydrogen, oxygen 1, and we have fluoride ion there. Okay, of fluorine element. Okay, so the fluoride ion is included. Okay, and in the reactant part, water is not included. The activity is 1. Only the hydrofluoric acid is included here. Okay, so in the reaction 1 is an example of homogeneous equilibria, wherein the substances are all in the same state, which is the gaseous state. Whereas reaction 2 and 3 are an example of heterogeneous equilibria, wherein the substances are in different states. In these cases, only the gaseous or the aqueous substances are considered in the expression for KQ. Okay, moving on, let us have more practice in writing your KQ expression. Okay, let us have the following exercise. We're asked to write the KQ for each of the following reaction. Again, the first step is you have to check if the equation is balanced. before you can proceed in writing the KEQ. And check the species that involve only gaseous or the aqueous substances are involved in the KEQ expression. For solid and liquid, they are taken as one. Okay? For number 1, we have phosphorus pentochloride producing phosphorus trichloride and chlorine gas. Okay, we check if we have balanced equation. We have 1 phosphorus, chlorine 5, 3 plus 2, 5. So we have balanced equation. So we take the numerator, the product as part of the numerator, as in this expression. So make sure that the main bar is between the equal sign. So the concentration of phosphorus trichloride at equilibrium multiplied by the concentration of the chlorine gas at equilibrium over the concentration of phosphorus pentochloride. Okay, since this is an homogeneous equilibra, all the species are involved in the expression for chemical equilibrium. Okay, moving on to the second example, we have hydrogen gas and oxygen gas producing water as the product in the liquid state. Again, since we have water here as your product, it is in the numerator, and since the activity for liquid and solid is 1, so we have 1. Okay, and we have a balanced equation. Okay, we check first again. By the way, we check first if we have a balanced equation here. We have 2 hydrogen, 2 oxygen, 2. We have only 1 here. If we multiply this by 2, that makes the oxygen balance here. However, the hydrogen make it in the product side is increased by 2. So we have to multiply this by 2. So, moving on. This is not affected by the coefficient 2 because 1 raised to any number is still 1. Okay, however, here the concentration of hydrogen is being squared multiplied by the concentration of oxygen. Okay, we extend the main bar. Okay, that is the property of writing it. Okay, next we have the reaction of water in the liquid state and carbon monoxide producing hydrogen gas and carbon dioxide. Okay, first we have to check if we have a balanced equation. We have 2 hydrogen, 2 hydrogen. Oxygen here, we have 1 plus 1, we have 2. We have 2 there. And we have carbon. Okay, we have a balanced equation. Okay, in the product side, we have hydrogen and carbon dioxide in gaseous state. So, all the product species are involved in the numerator. Okay, so the concentration of the hydrogen gas is multiplied by the concentration of carbon dioxide gas. And in the reactant, the water in liquid state is taken as 1. So you have carbon monoxide only in the denominator because this is taken as 1. You don't need to write it. Any number multiplied by 1 is the quantity itself. Okay. Now for the third one, we have here carbon in solid form with react with carbon dioxide giving you carbon monoxide. Okay, we check if the equation is balanced. We have here 2 carbon, 1 plus 1, and we have only 1 here. So we touch the coefficient at the start of the molecule, carbon monoxide. Then we check for oxygen 2, 2. So we have balanced equation. Okay, so the numerator will pose of the product raised to its coefficient. We have only 1 product, carbon monoxide, raised to 2. And the denominator, the reactant, since this is solid, again, this is taken as 1. Any quantity that's multiplied by 1 is the quantity itself. So we have in the denominator carbon dioxide. Okay, and we have one coefficient, okay, for carbon dioxide. Okay, moving on. For the PIP example, we have your barium sulfate solid, okay, producing barium oxide, another solid product side, and sulfur trioxide in gaseous state. So we check if we have balance equation, 1 barium, sulfur 1, oxygen we have 4, and on the product side we have 1 plus 3, 4. So we have a balanced equation. So since both barium sulfate and barium oxide are solid, only sulfur in the gaseous state in the product side is involved. And the denominator here will be 1. So the expression is sulfur trioxide because the denominator would be 1. Any number divided by 1 is the number itself. Okay? So you should express it correctly in a simplified form. Next, we have zinc, positive 2 ion, aqueous, and the hydrogen sulfide, gaseous state. The product is zinc sulfide, solid, and hydrogen ion in an aqueous solution. Okay, we check if we have balanced equation. We have zinc 1 on the product side, sulfur 1, hydrogen, we have 1 here, we have 2, so we attach 2 here to balance the number of hydrogen. Then next, we write the chemical equilibrium constant. Okay, so the product, you have solid here and aqueous, only this species will be involved in the expression. So we have your hydrogen ion raised to 2, which is the coefficient. On the reactant side, we have the zinc ion in aqueous, so it will be involved here. You have positive 2 raised to 1. You don't have to write that. And we have multiply by the concentration of the hydrogen sulfide, which has also 1 coefficient. You extend the main bar. Okay. It is incorrect to write the main bar after this only. You should extend it covering all the product. Okay, now next, for the 7th example, we have calcium ion in aqueous solution, carbonate ion in aqueous solution, and producing calcium carbonate solid. Okay, this is an example of the precipitation of calcium carbonate from its ion. Okay, so since the product is solid, the equation is already balanced, so we have only 1 in the numerator. And we have here in the reactant side, in the denominator, we have calcium positive 2 raised to 1 multiplied by the calcium carbonate negative 2. Again, we extend the main bar, and the main bar should be written between the equal sign, not above, neither not below the equal sign. Okay, for the 8th example, we have here your lead sulfate, solid, ionizing to lead ion, plumbous ion in aqueous, and the sulfate ion. Okay, we have checked if we have balanced equation. It is balanced. Okay, since the numerator, which is composed of the reactants, are all aqueous, which are involved in a chemical equilibrium expression, and the denominator from the reactant is a solid, the denominator is 1. So we don't need to write a bar here, but the expression would be the concentration of the plumbous ion multiplied by the concentration of the sulfate ion in the aqueous solution. Okay? That is how we write chemical equilibrium constant or chemical equilibrium expression. In the next episode, we will learn how to calculate or involving this chemical equilibrium expression. Okay, I hope you have gained the skill in writing the correct chemical equilibrium constant based on a given reaction, reaction. Okay, for a specific balance reaction. That's all for this episode. And I hope you will carry on that skill that you have gained in this episode to the next episode, which involved calculations involving equilibrium constant. Good day.